Okay, we are good to go. Good morning, good afternoon, everyone. Welcome to today's webinar on nozzle check valve flow simulation using Autonomous Valve CFD. We are thrilled to have you with us today for this session. Whether you're a valve designer or a CFD engineer, today's webinar will provide you valuable insights in how to leverage latest CFD technology in valve design and optimization process. So let me introduce myself. Uh, I'm Praveen. I'll be your host today. I've been working in this field of CFD for the past 15 years, helping businesses bridging the gap between technical and market needs. So at Simulation Hub, I have been working for a wide range of industries, including valves and HVAC systems, etc. So I'm delighted to introduce today's speaker, Akshay Dorle, the business manager of Autonomous Valve CFD at Simulation Hub. Akshay brings over multiple years of experience at CC Tech, where he leads client engagement, technical guidance, and product support for AVC. He works closely with the valve manufacturers to ensure they successfully adopt the onboard them on this platform. Akshay holds a master's degree in mechanical engineering from NIT Silchar and has a solid foundation in CFD, making him the perfect expert to share valuable insights on this topic. So along with us joining like Joel and Manas, who has brought you a lot of interesting case studies, a lot of contribution went into making this presentation. So yeah, thanks, Akshay. Move ahead. So yeah, so today the agenda of today's webinar is we'll start with the basics. Like we'll talk about check valves, what are the applications, why and what, everything, and then move to the today's topic like nozzle check valves, and then we'll cover the basics of that. What are the key parameters, that play like vital role in design, optimization of nozzle check valves, and as well as sizing of them. And we'll, in the context of obtaining those key parameters, we'll introduce Autonomous Valve CFD, and then we'll present some interesting case studies and some real life success stories of using AVC valve manufacturers using AVC in their design process. So at the end, we'll have a Q&A session. So while the session is going on, if you have any questions or anything, use the chat window or the Q&A section to post your questions. We'll take those questions towards the end. Going next. So for those who are new to Simulation Hub, like what we do, who we are. So Simulation Hub is a AI-powered autonomous simulation platform. It is cloud native CFD simulation application for designers. So we have multiple apps developed on this platform. In the context of today's topic, so Autonomous Valve CFD is the product designed for valve design engineer. Okay. So more on the product in the middle of the webinar. So right now, without further ado, I'll hand it over to Akshay. Akshay, over to you.
Uh, Thank you, Praveen. Thanks a lot for that wonderful introduction to today's topic and wonderful introduction to our young team and myself. So let's begin for today's webinar, which is nozzle check valve simulations in Autonomous Valve CFD. So before jumping into the topic at hand, which is nozzle check valve, we'll start with a few fundamentals first. We'll try to understand what is check valve, then where does nozzle check valve fit in these check valves, and then we'll further see how CFD is advantageous for de designing a nozzle check valve and other things. So without further ado, I'll just go to the yeah. So check valves are at the heart of protection of your expensive equipments, especially when there are chances of flow reversal. So before jumping into technical things and engineering related things, I would like to point out that all of us have a check valve, or let's say a set of check valves inside us. It's the heart. So heart has different chambers and it has few walls. So these prevent reverse flow inside the heart itself. So, even nature is very cautious about how to get flow in a single direction without having reverse flow, which can cause a lot of problems. So similarly, to protect equipments, expensive pumping systems, pipelines, and other industry processes, check valves become a very essential equipment or a component in the entire uh, process system. So let's just see where check valves are used. So they are used in pump discharge lines. So this is one of the most common examples of where check valves are used. So when pump suddenly stops, so when pump trips, or let's say there's a power outage, something, there's a tendency that the flow would reverse and to stop the flow going in the reverse direction inside the pump and damaging the impeller, or causing a whole lot of other problems. We install check valves in pumping systems. We have booster pump systems which have multiple pumps running in parallel. So again, very important to use check valves or to have check valves in such systems. Desalination plants, refineries and chemical plants. So any process which has multi-stage equipment uses check valves very strategically. So in refineries and chemical plants, this becomes a very essential component. Power plants, so feed water, boiler systems, condensate systems, all of these have check valves. Coming to the next one is district cooling. So in these systems, there are long pipelines, and in case of reversal, this could disrupt a lot of things. So even in district cooling and heating, so these are a very essential component in the process. Then water pump, water distribution systems. So again, in many systems, check valve performance directly impacts the reliability of the whole plant. So once we understand this, it becomes obvious as to why proper uh, design of the check valve and the proper sizing of the check valve is essential, as it's related to such critical industries, and it prevents a very significant phenomenon of flow reversal. And later we'll see uh, water hammer and all of these things, so how it does those things. So moving on to the next slide. Just give me a second. So these are the types of check valves. So a very well-known example of check valves is the swing check valve. So it's just a disc hinged at the top, and as the flow takes place, the flap or the disc opens and it lets the flow in a single direction. So all check valves are by design unidirectional flow components. Then we have lift type check valve. So again, it's a lifting type component. It will be pushed from the downstream side by the force of the fluids and the pressure difference between the upstream and the downstream sides. And it again is a unidirectional flow system. We have piston check valves, which again unidirectional, used in different applications, different industries. So this is just a collection of check valves, you could say. These are the various types of check valves depending on the industry, depending on the application. You would use swing check valve or disc check valve or dual plate check valve. Then we have ball check valve. So this again is a spring loaded one. There's also one which has a floating ball inside the valve. So there are these. Then we have today's the topic of today, which is nozzle check valve. So again, it's a unidirectional check valve. We have dual plate check valve, tilting disc check valve, and Y type check valve. Again, completely depends on what type of application we are using them. So let's move ahead. Let's see what uh, the importance of nozzle check valve. So yeah, nozzle check valves are also called as non-slam or silent or axial flow check valves. So as you can see in the video animation running on the right side of the screen, the travel of the disk is in a linear fashion. We'll see in the further slides why this is called a non-slam check valve. So we'll understand the phenomenon of slam, then why nozzle check valves are kind of silent or non-slam. And so these check valves are spring guided. So the disk moves in a straight line and it is loaded with a spring to resist the motion of the flow. So once the flow or the pressure difference is uh, correct or as per the design, the valve will open only for that flow condition and it will stay open till the flow rate or the pressure difference is met with the design conditions. Let's say in case of flow reversal, the spring will push the disk back again, and again it will prevent the expensive equipments and the expensive pumps and impellers and all of the other things by preventing reverse flow. Uh, this check valve becomes a very new kind of a design, or you would say a very uh, critical design, because it moves very quickly due to the springs which are used to prevent the backflow, and it's a linear travel, so the travel itself is also less. So let's move and understand what exactly uh, are the details that go into the design and understanding of the nozzle check valve. So as I referred earlier, nozzle check valves fall, or they're also known as non-slam or silent check valves. So to understand what is a non-slam check valve, we'll have to understand what is a slam. So what's slamming? So whenever in a traditional swing check valve, as we are seeing here in the image, so in case of a swing check valve, let's say the uh, swing check valve is running under fully open condition and there's a pump trip, the flow starts reversing and the disk will gradually start to close the valve, and as the reverse flow increases, a large quantity of or a large column of fluid will hit against its back and it will cause an abrupt stop or an abrupt pause in the reverse flow of the water column in the pipe. So this instantaneous stop gives a very loud hammer like noise, and this is usually referred to as water hammer. But the interesting thing is that it's not, the slam word is not related to the slamming of the disc on the valve body or the components of the valve. It's actually the sound of the pipes stretching inside this abrupt pressure wave, or the pressure, abrupt pressure rise inside the pipeline. And it almost sounds like a metallic noise. So even resilient seated walls and metallic seated walls will have almost the same sound in water hammer. Uh, so as we have seen, water hammer takes place, it causes a huge spike in pressure. This is referred to as surge pressure, and it travels as a shock wave inside the pipes on the downstream end. and the magnitude of this pressure is calculated by Joukowski's equation, which is given in here, which is rho times C times VR divided by 10 to the power 5. So rho is the density of the material of the media. C is the wave velocity. So this could be a combination of two things. It's the combination of your velocity of sound in the fluid medium as well as in the pipe. And VR is the maximum reverse velocity. So we can calculate surge pressure, or from surge pressure we can calculate reverse velocity using this equation. So we have seen what's slam. We have also seen why nozzle check valves are called non-slam valves. So we'll just see what are the advantages of nozzle check valves. So nozzle check valves, due to their design, they provide very fast closure of valves due to the springs. They act very quickly, and also the travel is very small. So that's one of the advantages. Second is it's very compact. It's suitable for various orientations. You might not be able to use nozzle check valves, swing check valves in, say, vertical applications, or when the pipelines are inclined. All of these could change the way in which the valve will behave, even if you might have considered the correct sizing parameters according to the flow, but the orientation also matters. So nozzle check valve is pretty flexible with the orientation. Again, because of the springs, it remains closed even in vertical and horizontal orientation. It provides better long-term efficiency. So nozzle check valve has a streamlined design, or they are designed in a way such that the pressure losses are minimized. And due to this, the total life cycle cost of the plant, so let's say it's a refinery, it's a water management system, the total life cycle cost is lesser as compared to traditional swing check valves or dual plate check valves, just because the head loss itself is pretty less. The disadvantages would be it's sensitive to sizing, so you must size it pretty well, and your spring selection matters a lot, as it's the controlling component of the valve under reverse flow. So sizing the spring becomes very important. Also in the normal flow conditions, which is when the valve is fully open, spring should be appropriately sized. We'll again see this in detail. Needs a good minimum velocity and a good upstream flow profile. So again, the flow profile should be uniform, fully developed for its proper operation. And initial cost is high. So as compared to other swing check valves or dual plate check valves, the initial cost of nozzle check valves is high. But this is the initial cost. If you look at it in the long term, again, the total life cycle of cost of the plant is much lesser as compared to when swing check valves or traditional check valves might be used. So again, it becomes a thing about economics as well as your design and sizing. So we have to be careful while choosing the check valves, and once chosen, it should be sized correctly. So we'll look at a few terminologies about check valves. As we have seen in the nozzle check valve, it must have some initial velocity. So we'll go one by one. So first is the cracking pressure. So as the nozzle check valve has a disc, and behind it there's a spring. So it in general, it's a pre-stressed or pre-compressed spring, so that it's completely closed. It gives the proper bubble shut off sealing in case of no flow conditions. So the cracking pressure is the minimum upstream pressure required to start the opening of the valve. So it's pretty straightforward. If the cracking pressure is too high, the valve will not open properly, and if it's too low, it will open at a lower pressure and it will oscillate and give rise to chatter and all of the other things. So spring becomes a very important critical component while designing your nozzle check valves. Critical velocity is one of the parameters for nozzle check valves, which is again very critical and essential. It is the velocity required to open the valve in a fully open condition. So critical velocity applies to the valve when it is in complete, it's fully open, and that should be the minimum required velocity to open the valve. Again, this becomes very essential in designing your nozzle check valve, because say your critical velocity or the velocity of the uh, line or the process fluid doesn't match your critical velocity, the valve might not open correctly. And again, since the valve is partially open, it gives to a higher pressure loss, and then this in turn affects your economics and your total life cycle cost of the plant as well. So it's very essential that critical velocity is uh, chosen correctly, and for this critical velocity, you size your valve and size your springs correctly as well. So moving on, there's a term called zeta coefficient. So zeta coefficient is essentially a pressure loss uh, coefficient. You are quantifying your pressure losses for your valves, and it becomes essential when you're comparing different designs of the same nozzle check valve, or you're choosing different kinds of check valves. Zeta becomes a very essential parameter in choosing and sizing your valves. Uh, Conventionally, and as we have seen it in the industry as well, the zeta coefficient is the least for nozzle check valves. So swing check valves will have a slightly higher zeta coefficient, which will give rise to the higher pressure losses and higher life cycle costs. So that's about zeta coefficient. And then there is sizing curves. So these are the dynamic characteristic performance curves for check valves specifically, in which the valve is chosen based on the minimum, the maximum reversal velocity uh, that you have calculated, let's say by Joukowski's equation, or you have that data for you, and then you decide the valves based on how quickly or how slowly you want your valve to react to this flow reversal. So this graph is used for choosing your valves, choosing different check valves, and also within nozzle check valves, you can have different designs, and you can compare which fits the best. So essentially, you would like the uh, valve or the nozzle check valve which reacts at the lowest critical velocity. So, or the lowest maximum reverse velocity. So it would be the red curve here, which is the nozzle strong DN300 Thorley. So, but again, it's an engineering problem in which it becomes very critical as to what's the application like, what's the economics of the system is like. So again, ideally you would want to choose a low the fastest responding nozzle check valve, but again it's your choice as to how you uh, again, depending on application and economics. So why should we use nozzle check valves? Why you know we have chosen this topic, as well as we saw from the dynamic characteristic curve, why nozzle check valve performs so much better than the other kinds of check valves. And this was extensively studied by Thorley, and he came up with three parameters that should be minimized, so as to speak, so that the check valve will be the most ideal in terms of dynamic response. So the first is the disc should have low inertia and friction. So this basically means it should be a lighter material or a lighter design, and it should have less friction, so that in case of reversal of flow, you could the valve can react quickly. So in swing check valves, there are instances where the hinge pin gets locked, and it doesn't react as quickly as it should. So that's one. So if you then next is the travel of the disc should be short. So if you look at this swing check valve, it has to travel in a curved path. It takes longer to get from point A to point B. Similarly, in case of dual plate check valves, they have to travel along a curve, and they have to, so it's a longer path. Compare that with axial check valve. Axial check valve has a very linear, minimal distance to travel, which is again assisted by the springs. So it becomes very, very quick in responding to flow reversals. So if we look at the three parameters, so the inertia should be low. So swing check valves obviously is not falling in that category. The minimal travel, it should be low. Again, both uh, swing check valve and dual check valve are not there. And spring assistance. So again, no, conventionally, swing check valve doesn't have a spring assistance. Dual plate check valve doesn't have, but spring assistance like axial check valve is designed with a spring. So on all three parameters, nozzle check valve is a good design and a good engineering solution when used in flow reversal uh, conditions. So we have been through a lot of definitions, a lot of terminologies, and we had a look at what are check valves, what's a nozzle check valve, what's a slam, what's a non-slam, why check valves, what are the key parameters that are required in designing the check valves. We saw why nozzle check valve is better than the other two designs. So here we'll understand uh, the other key parameters that could be used or that are used by manufacturers to select check valves and size the check valves. So obviously there's flow coefficient. With any valve, we have to have the proper sizing based on flow coefficient. So that's one. Second is the KV versus zeta curve. So again, we saw in previous slides that zeta is the coefficient that quantifies your head losses. So in this image, you can see that this is a zeta curve plotted against a pressure drop. And the next is critical velocity. So again, as we saw in the previous slides as well, critical velocity in nozzle check valves is one of the parameters that we must be very sure while designing. And for this critical velocity, the spring stiffness or the choice of the spring also becomes very essential, so that when it's in the industry, when it's in the process condition, the valve opens to a fully open condition for that critical velocity and any velocity of the fluid beyond that. As we saw earlier, to size the valves and to choose between designs of the same check valve or between different types of check valves, we saw the dynamic characteristic curve. So at the moment, as we'll see, CFD will be able to give you all of these coefficients. So flow coefficient, as we have seen in the past webinars as well, that is what AVC does. That is the USP of AVC. You can give it any valve, you'll get the CV curve. You'll get the zeta versus KV versus zeta curve as well. Again, it's a quantification of head loss. So pretty straightforward. Determining critical velocity and spring stiffness. Again, CFD will be used to determine this. As of now, dynamic characteristics of the valve, they are modeled in the industry based on, let's say, 1D modeling or very complicated transient CFD simulations. This at the moment would be currently out of scope for us to discuss. So we'll discuss flow coefficient, KV zeta curve, and critical velocity and stiffness. So we'll start with flow loop testing. So as it is the case with any valve, to get the flow coefficient, to get the zeta curve, you might need to do flow loop testing. So flow loop testing, again, it's it is used to determine the flow coefficient, and again, the flow loop standards and the flow loop tests that are conducted are in accordance with the following standards, which is IEC and NCVs standards. And in India, there's FCRI that does the flow loop testing, which is very popular. And in the US, it's the Utah Water Research Laboratories. So one way to determine the coefficients required would be flow loop testing. So we'll go through the cycle of how this would happen. So in case you are venturing into designing a new check valve or a new nozzle check valve, you would start with what are the design requirements, what's the target CV. The CAD or the design engineer will take this design, use his expertise, design a valve, a prototype will be manufactured, then this will be transported to a testing facility, and the results are reported, which will give you the CV and the other parameters. This takes weeks, if not months, to do. So even if the designing to manufacturing part might be straightforward, there might be a case where the testing facility has a long waiting line, has a long waiting list to test your valves. So again, it can take from weeks to months. The other challenges in flow loop testing are it will give you CV, but no more insights. You can't visualize flow separation. You can't visualize low pressure regions, which give rise to, cavitation and stuff. So again, next is the design and the cost and the time. It's very high because let's say you want to redesign the valve, the CV was not correct, or it was not in accordance with the design CV. So you'll have to again go back to the design stage, again do the prototyping, again do the testing. So again, a lot of time, a lot of money goes into this. And then it's the resource limitation, in the sense very large size of valves. There could be a chance that such large designs might not be even be able to possibly test in that testing facility. It could be due to the size itself. Second is again transporting such a large valve and getting it back. So all of these add a lot of challenge in physical flow loop testing. Then there are alternate methods to getting the flow coefficients or other parameters. So we'll see that. So we already saw flow loop test. The second is analytical methods. So again, it's fairly accurate, I would say. Time is very less, cost is very less. Skill to get these parameters is very less. You just have to input the various numbers and it will pop out the CV for you. But again, this works only for simple designs, very standard designs. The next is numerical methods or CFD. So accuracy is very close to real life scenarios. The time required is more compared to analytical method, but is much less as compared to the physical flow loop testing. The cost, yes, definitely. There's the infrastructure cost for numerical method. So you have to have a high performance computing or a workstation. You have to have license of the CFD software, and you must also have a skilled professional, CFD professional, to actually use these tools and give you sensible answers or sensible results. As we spoke in the previous slide, analytical methods are the cheapest, the least time taking, but again, limited to simple designs, limited to not having those insights regarding turbulence, regarding cavitation. All of these things might not be possible or are not possible in analytical methods. Then, depending on the size, depending on the design, you have to have a lot of correlation factors, lot of adjustments to your standard formulas. And again, this could give you a right value, could not also. Then comes CFD. So CFD is the science to predict flow phenomenon. So specifically fluid flow, heat transfer, chemical reactions, any transport phenomenon that you can model. This is done by modeling mathematical equations and solving numerical methods on a high performance workstation or a high performance cloud. So again, won't go into much details. What it essentially does is solves the Navier-Stokes equations, which is the continuity equation and the momentum equation. Your entire fluid domain is broken down into small volumes, and equations are solved on each of these volumes, and then flow parameters like fluid flow, some scalar transport, heat transfer, all of these are integrated on these small volumes. So again, you need a professional to do a CFD. So what is the advantage of CFD? CFD gives you the insights. You actually can look inside the valve almost to see what kind of flow phenomenon is taking place. So if you see here, there's acceleration of flow, there's recirculation here. All of these insights would be lost in analytical methods. They won't even be thought of to visualize in actual flow loop testing, but this becomes essential as you can see where it might cavitate, where it might where the flow might separate. So all of these insights can be done through CFD, hands down. So the conventional CFD process, you have a 3D CAD file, you extract the fluid volume, you generate a high quality mesh, then you set up the boundary conditions, and you use a high performance workstation, HPC, and you solve the equations using your CFD solver, which could be commercial, single license. It again depends on what sort of license you have, and at the end you get a CV curve, as you can see here. So along with CV curve, you also get qualitative insights like acceleration of the flow, flow separation, flow recirculation. The challenges with CFD are you need an expert to actually perform the right simulation. As we have seen, it deals with a lot of mathematics, it deals with a lot of numerical methods, it deals with a lot of understanding and knowledge about computing systems. So you need to have a well-rounded CFD professional to actually give you sensible results, because there are many parameters that could go wrong. You need a high-performance workstation. The license cost. So commercial CFD licenses are pretty expensive. So these are the challenges with conventional CFD. So to address all of the challenges that we saw in conventional CFD, which is expertise, setup, license cost, we have AVC. AVC is a specialized valve virtual flow loop testing application. It is specifically for valves. We again follow the same standards that actual flow loop testing follows, which is the ANSI, IEC, and M49 standards. What you get at the end is the valve performance parameters, which is CV, CDT, and cavitation index, the incipient cavitation index. And it is powered by three powerhouses of technology. So the visual part, which is the viewer, where we can see the CAD file and all the contours and all the flow insights and the various openings. All of these things are we are able to visualize by the power of Autodesk Platform Services, the Autodesk Viewer. The CFD simulations run on high performance computing infrastructure, which is powered by AWS. So AWS is the infrastructure for us, and the solver on which the AVC depends is the OpenFOAM solver. Again, this is very popular in academia and industry. It's an open source solver, and it's very versatile. It's the state of the art when it comes to open source softwares. And with these three powerhouses, we have our AVC. So this is the usual workflow of how a simulation would take place in AVC. You just input CAD model, flow direction, and openings. The Autonomous Valve CFD, which is powered by all the complex logic of conventional CFD, is inside this app, which we have written the algorithms for, and we have designed the app such that. And what we get at the end is flow insights. So it could be velocity contours, it could be flow lines, it could be surface pressure, it could be minimum pressure location. You could have a multi-stage valve, so you could visualize the multi-stage pressure loss. You also get, apart from all of these qualitative results, you get a graphical and a tabular representation of flow parameters, which is CV, CDT, head loss coefficient, incipient cavitation index. All of these qualitative and quantitative results are consolidated in a report, which is again generated autonomously, which is available after the simulation is done. So that's the power of CFD, or the Autonomous Valve CFD. Supported valves on the platform are, we support almost all control valves and isolation valves. So you can check this slide out. We have rotatory motion valve, linear motion valve. We have almost all ball valves, butterfly valves, globe valves, axial flow check valves. So as the topic of today's webinar is axial flow check valve. So when users have to use the platform to design their valves and to study the CV, KV, CDT for their nozzle check valves, we would go with axial flow check valves. Moving on to the next one. So here we have done a demo. So we'll just quickly jump into the demo. So this will give you an overview how AVC works. So it's a web-based application. This is the dashboard of your account. You will start with creating the simulation. You will just give it a quick name, axial flow check valve. You will give it a description, and so we start with, there are 4 stages for simulating any valve. First is the geometry upload stage. So we'll just upload step file. So we have step file, we support step file, parasolid file, .sat file. All of these CAD formats are supported. And we just specify the valve. We specify what type of motion it is, what type of valve it is, what's the size, what's the roughness. Once it's specified, we move on to the next part, which is the moving part selection. We, again, with the interactive Autodesk Platform Service viewer, we can easily select the body, which is the moving body. We can select the shaft and we'll give it a maximum stem travel. And with this, it will populate all the openings and we can move to the next part, which is the valve directions stage. So, sorry, the flow direction stage. So once we have selected the moving parts, we'll move on to the valve. Just a second, there seems to be something. So this is the valve pipe connection stage. We just select the inlet and outlet pipe. Then this is done. Once this is done, the job of the engineer or the designer is done. We submit the simulation and the autonomous platform will take care of all the simulation runs. So it will go through all the conventional CFD steps autonomously. Once it's done, we get the post-processing of results. So right now we are seeing streamlines. So we can visualize streamlines. You can also create cool animation. You can post it on your website to show that you have the capabilities of CFD. You can show how it will perform in almost real life situations. We have the surface pressure. We have the velocity contours. So all of the visualization is integrated into the web platform itself. You can visualize, get insights, you can see flow is accelerating here. All of these insights can be extracted from the app itself. Then we have the tabular values of the performance curves. So it's KV, CV, we have tabular, and we have graphical representation. And at the end, we also have a consolidated report. So this is how the report will look like. It will have all the valve details, the executive summary, the objective, the methodology of CFD, the formula for CV, and the qualitative results, which would give you the insights of the flow. So we have pressure contours, we have velocity contours, and all of this is generated autonomously. So this is the power of Autonomous Valve CFD. You get qualitative and quantitative results in a consolidated report without any expertise in CFD. So moving on, we have a case study for you guys. So as we spoke few slides back regarding critical velocity and discussing zeta coefficient and spring stiffness, we actually did a small case study in which we were able to predict the spring stiffness, the zeta coefficient. So we'll just jump right into the case study. So choosing the right spring for the required critical velocity. So as we have seen, the controlling component of the valve is the spring itself, and we have to choose or you can say have the correct spring stiffness so that the valve operates correctly. So we have done this using a very simple force balance. So we just determined the hydrodynamic force from the CFD simulation. We balanced it with the spring force at full opening. And for various critical velocities, depending on the force, we get various choices of spring. So as we have seen, the spring can be determined from the choice of critical velocity. Let's say you want to go with 2 meters per second critical velocity, or that's how the process conditions are set up for you. So that will give you the insight. Okay, my spring stiffness needs to be somewhere around 50, slightly lesser than that, so that it will compensate for friction and other small losses, and the valve will be able to completely open with that spring. These are the qualitative and quantitative results that we extracted. So as we have seen earlier in the slides where we discussed the parameters or what's printed by valve manufacturers in their catalogs. So there was a zeta curve, there was a CV curve. So again, CV and zeta curves can be obtained for the valve using AVC. So not only for full opening, you can actually get it for all the intermediate openings as well. So again, this becomes very essential. It's very powerful because conventionally what manufacturers might print on their catalog is just a full opening CV and zeta, and you might want to understand, okay, what might it be in 50% opening or 80% opening. So with AVC and CFD, you can actually determine that and have a much better understanding of how the valve performs in those conditions. So these are a few of the leading manufacturers in valve nozzle check valves. So Magwin, Sierra, Trillium, Redpoint, and so all we can support axial check valves on our platform now. We can readily obtain the CV curve, the incipient cavitation indices, and the parameters. So moving on to validation study, I would like to bring on Praveen to give us the insights on the validation study.
Yes.
Yes, Praveen.
Thanks, Akshay, for covering. It's a wide topic, right? Like, so it has a wide and depth as well. So moving on with validation studies, we have validated our application results with much like with lab results from FCRA and Utah Water Research Laboratories for a wide range of valve types and valve sizes. So what we observed is like the results always fall, most of the time falls in the range of like plus or minus 5% deviation. So there are some corner cases where the size valve size is low, but still it's in the near the 10% deviation. And so overall 90 plus is the accuracy we have observed. And on top of this, what we do is when anytime we engage with a new customer, so we we run a pilot kind of project kind of thing to gain the trust. So if they have their own lab tested data for any of their design, we validate it using the application, and then we move ahead with the other process. So moving ahead. So what happens, it's just a summary of things like what already Akshay mentioned. So you upload the CAD model, select the moving body, and define the inlet like flow direction. So this is the input you give. So what we do with this input is next. So what happens in the cloud? So it does all the conventional like CAD cleanup, mesh generation, and the simulations on the cloud. Next, and what you get as output is 3D results like the contours and qualitative results, quantitative results, and the PDF report, which is ready to submit to the end client. Next. So what goes behind the scenes is when you upload your valve model to AVC, so it assigns 36 core dedicated machine EC2 instance on Amazon like web services, and then the conventional process, CFD process. So it uses simulation of APIs for doing the CAD cleanup or extracting the fluid volume and do the meshing and solve and monitor and convergence. So all these things are done autonomously, and then you get to see the results on the web browser. So simulation results on the browser. So it's not just for that opening. So if you have multiple opening conditions, so each opening runs parallelly, and at the end of the 1 hour time, you get the results and the report. So not just this, let's say you have two designs and you want to compare those two designs, and there is no dependency or waiting in queue or anything like that. So unlike the desktop software where the number of license becomes a bottleneck. So here it's a web platform, so it runs parallel. So it's a short, yeah, move ahead. So it's a short comparison of the conventional and the simulation of process. So in the conventional process, so the dependency on simulation of experts and the manual processes causes the delay, and also adding to top of it like limited in-house resources. So the number of like the time required to obtain the results is in days, and whereas on the simulation of side, we run the process on the cloud and as well as autonomous. So that makes sure like the results are obtained in hours. Okay, typically it takes 1 to 2 hours depending on the size of the valve and complexity of the valve. Okay, moving ahead. So I use this metaphor to make a comparison. What happens is like it's like when you want to plant a simple sampling at in your garden, which tool would you choose? So is it a kind of JCB or some kind of heavy machines, or just a gardening tool, right? So for valve simulations, you need something very handy and designed for that particular thing, not the generic CFD tool. So if you take a generic CFD tool, it can solve a problem like a pipe flow to aerospace and combustion and whatnot. So you have all the capabilities, and it's unnecessary chaos to the user as well. So our AVC is designed for the particular job. So here is a short a view on customer success stories. So these are our customers across the globe. They flow management, Sierra, every Del Wall, flow tide. So we are still adding more. And then I have picked two cases for today. So Bray International. So Bray is a very big valve manufacturer in North America. They have design centers in Houston and Bangalore, etc. And the challenge which they had is they already had a do flow loop test, which takes them 3 to 4 months, including the prototype manufacturing and things. And they already have had an in-house CFD team using the conventional or CFD software, and that used to take up to 5 days. And the CFD expertise were less in number, and they were overworked by the number of designs they have in queue. So this is the challenge they had. And then the solution which we came in, and then we introduced Autonomous Valve CFD. They adapted it. All the designers are now doing the CV capacity testing, simulation, everything. And the experts are doing the noise and the very advanced and complex level simulations. But the flow capacity estimations are like simulations are done by the designers themselves. Yeah, moving ahead. So we do often visit our customers, conduct trainings. We listen to them, the pain points, and then we add more features to improve the workflow. Going ahead. So these are some kind words from Brindesh from Bray. Um, so going ahead. So this is another success story like where we partnered like Sierra partnered with our simulation of team for finding out the for critical velocity, what is the right spring stiffness, and then the KV versus zeta curve. So this is like one of the products. So multiple designs we have collaborated with them, and then we helped them in achieving the results. Yes. So what's ahead? So you can start, the next step is you can start trial subscription, which is normally 15 days and 20 simulations you can perform. 20 valve openings, I would say. 20 CFD simulations you can perform. And or you can, what you can do is you can schedule a call with our expert. So the link is available on our website, and mention specifically about this webinar attendance, webinar like that you have attended this webinar. Akshay, go ahead. So for this, exclusively for this webinar attendees, we are extending that 15-day trial into 1 month and then additional simulation credits. So you can explore more and experience it for yourself. Next. So a special thanks to our young team again, who contributed in all of the backend. They were acting the backend team. They are the backend team. So yes, thanks. That's it from our side. And yes, we understand already we spilled out of our intended time limit, but yes, the session is open for question and answers now. So we had few questions in the Q&A box. Mostly it is on the the about the nozzle check valve side. Okay, so I'll read out one which is on the kind of CFD side. Already Joel has answered, but still I'm not sure whether other attendees can access that. So one of the question was, how do you determine the hydrodynamic forces to select the right spring? So once the simulation is done, the CFD simulation is done, the hydrodynamic forces can be extracted from the CFD results itself, and then that compared with the what Akshay mentioned, like a force balance. So based on that, that is the the force, the spring force required, and then for that length, the length compression length is fixed, and then you can select the stiffness, spring stiffness. You can calculate from that hydrodynamic force. Okay, so that is one. And okay, there is one more question coming up. Oh, okay, it needs some language translation. Maybe. Okay, so never mind. So usually, typically, what we see is what is the how it is compared to it's about the validation or some part. So Akshay, can you share the screen and go to slide number 63?
Sure, Praveen. Give me a second.
So meanwhile, if you have any other questions, you can write to us. You can put it in the chat, or you can write to us on the chat window in our website, simulationup.com. So we'll connect back, and then the recordings of the session will email you after in a day or two. So you can again access them.
Just give me a second. I'm there. 63, yeah?
Yeah. So meanwhile, we got that question in English. So is there a mathematical model to determine the hydrodynamic force that has been got from CFD? Not really. Actually, the CFD simulation directly, it's a post-processing technique through which we can get this hydrodynamic force. I'm not sure there is a mathematical model or something separately other than CFD. So once the CFD simulation is there, then it's there, it's done. The results are there. So you can it's just a post-processing tool which can extract the surface integrals and hydrodynamic force of the moving bodies. So the standards what we follow is the ANSI ISA standard and IEC and AWA, and then we also refer verification and validation in CFD. So ASME 20. Next. So this is the behind the scene thing. So the CAD cleanup, the process, the algorithm identifies which gaps to close, which gaps to keep, and does the CAD cleanup and fluid volume extraction as well. Next one. So if you see the mesh, so it's almost like it's same as that of the conventional meshing process. So it has all the mesh densities to capture the geometrical gradient as well as the flow gradients. So also we have the prism layers to capture the boundary layer on the valves. So if you see the mesh density near the moving body as well as upstream and downstream of it, you can see variations in the size, right? So that is to capture the small flow separations and also the gradients expected. And also on top of this, the algorithm runs the mesh quality checks. It runs its checks for non-ortho, skew phases, wrong-oriented phases, and then finally it improves the quality and gives you the things. So the point I try to make is like go to the next slide. So all the process and steps we follow in a conventional method is followed autonomously in the behind the scene. Okay, so that's what the residual convergence monitor, all those things, even the turbulence model selection as well as the Viper's criteria check. So all these things happens in the behind the scene. That's the thing. So yes, we already know like where there are lot of questions. There is one question about validate the values. Yes. So to validate the values, we have already validated it with set of lab test data. But Ahmed, like as you mentioned, if you are interested, we can connect separately. And if you have some lab data for your valve design, we can conduct that validation study separately. Hmm, that's all. So thanks everyone for their time and be with us till the end of the session. Although it extended a bit, I'm glad to see a lot of people, still up. So thanks for your time, and we'll again connect back with another interesting topic in future webinar session. Thanks everyone. Thanks Akshay and Joel and Manas.
Thanks a lot.